Good morning, everyone, and welcome. Thank you for joining us today for this webinar. My name is Laura Roberts, and I'm the Ava Marketing Manager at PDS Group. For those of you who may not be familiar with PDS Ava, we build cloud-hosted software which addresses key limitations in existing reservoir modeling workflows. Today's session is presented by Matt Boyer, a senior geologist in PDS Ava's team who is currently supporting the development of Ava saturation. Water saturation is a key component to the hydrocarbon volume equation, and as such, uncertainties in its determination at log scale and application to reservoir models by saturation height functions should be investigated, as well as multiple or alternate scenarios, which should also be considered. Over the next half hour or so, Matt will look at ways at which water saturation is calculated at the well log scale and how saturations are applied in 3D space. We will explore the uncertainties that can occur and how these affect the calculation of hydrocarbon volumes. We'll kick today's session off with a little housekeeping and then jump straight into Matt's presentation. We've allocated a little bit of time at the end of the webinar for questions and discussion. If you wish to ask a question, please type it in the question box in your GoToWebinar control panel. You can type the questions throughout the webinar or save them right until the end, but we'll address them all at the very end of the webinar. Matt joined PDS Group in 2017 to lead the team who brings you over saturation. He has over 10 years experience working in the oil and gas industry. In that time, he has worked for Shell in the Netherlands and for Helix RSD and Fairfield Energy in London as a development geologist. More recently, Matt worked as a reservoir modeler for Merlin Energy. He has worked on the exploration and development of a range of assets across the globe, with a particular focus on the Ukraine, Nigeria, Niger, and the UK's North Sea. Matt holds a BSc in geology from the Royal Schools of Mines at Imperial College London and an MSc in structural geology and geophysics from the University of Leeds. So now, without any further ado, we'll turn the time over to Matt.
Thank you very much, Laura, and good morning, everyone, or good afternoon, depending on your current time zone. Okay, so in this webinar, we're going to have a look at some petrophysical uncertainties, or more specifically, we're going to be looking at water saturation uncertainty and the impact that this can have on our reservoir models, volume calculations, and just generally the way that saturation uncertainties creep into the saturation calculations. So I'm going to take a look at water saturation at the log scale. So we're going to be having a look at sort of the Archie, Indonesia, Samandu equations that we might be familiar with. Progressing to having a bit of a look at upscaling and some of the considerations we may want to take into account if we're going to be upscaling saturations. And then moving on from the upscaling, we're going to be having a look at saturation height functions, whether there's any uncertainty associated with a particular height function. We'll have a bit of a demo of Ava saturation just to give you a flavour for how quick we can be calculating height functions, so we can actually begin to look at uncertainty, if there is any, within a particular method. And then have a look at a few other uses for saturation height functions. What else we can actually use these for besides just modelling SW. And then at the end, hopefully draw some conclusions which might be of interest. So moving swiftly on. We're all pretty familiar with calculating hydrocarbon volumes, the inputs required to it, and suffice to say, porosity, SW are two of the key parameters to the hydrocarbon volume equation. So those are a couple of things that we tend to focus on when we're building our reservoir models. But what we're doing when we put in these properties into our models is we're actually applying, or we're modeling something that hasn't actually been measured in the reservoir. It's something that we infer from log measurements, core measurements, and things like that. So uncertainties can sort of creep in and can manifest at each stage of the way. So in terms of the measurement scale, we can get uncertainties at the measurement level, by which I mean, for example, whether the resistivity log's being corrected for thin beds, borehole, mud, etc. And uncertainties in the interpretation level, that's basically how we interpret the logs, which equations we use, and then also how we actually apply this stuff to the model, through use of saturation height functions, through use of upscaling, and so forth. So this is just a little diagram just summarising some of that stuff about uncertainty. So this is just an example of some of the uncertainties that can creep into our measurements. So we have things like depth, wireline versus driller's depth, for example, thin bed effects, reservoir heterogeneity, core measurements, for example, if the core's been damaged during well operations, issues with the cleaning drying process, etc. And I found an interesting stat by an SPE member who delivers courses on SCAL and CCA analysis, and he's saying around about 70% of SCAL measurements are generally not fit for purpose. So are we taking this into account when we're actually using the core data, which we tend to think of as truth and gospel? We're taking that into account when we're actually looking at our when we're using our core data. In terms of uncertainty regarding interpretation, so I'm looking at a few things together in this one. So there's some overlap with core measurements and the electrical parameters, for example, so things like the AM, N, RW that we need to use for the Archie equation. But we've also got right the way along from data acquisition, upscaling height functions that we use as well. So all the way along, right from the start, from when we acquire our well logs, when we get our core data, through to the volumes that we calculate, there can be systematic errors that kind of creep in, and that can get compounded. And do we actually realise the effects these might have on the volume calculation, the way that we're modelling SW in our reservoir models, and what are some of the things that we should really be thinking about and just be aware of, I suppose is the right way of saying it. So what we're going to be doing this weather is we're going to be looking at water saturation. Which seems like a small uncertainty. Maybe we shouldn't worry about it, maybe we should, but when you add it together with a bunch of the other small uncertainties, it can be a bit of a problem. So let's start to look at some of the issues that can creep into, say, the Archie equation. So, for example, one of the things that we're interested in is RT. So that's obviously the true resistivity reading. So it's usually generated. We usually get it from the deep resistivity log, but there's a lot of acronyms for that particular well log. So as you can see on the left-hand side, that's just a handful of them that I found from a particular website. Do we know whether we've got the right log? Are we using the actual deep resistivity reading? Are we using RXO? Are we using shallow resistivity? We need to make sure that we get the right one. Are we doing the right corrections for borehole size, mud invasion, shale thin bed effects, etc.? Have we got the right charts, which I just kindly borrowed from the Schlumberger log interpretation books? And then what we can see is actually if we're correcting things or not correcting things, that can actually impact on what we're calculating. So what we have in the top picture over here on the right hand side is the uncorrected resistivity versus the corrected resistivity at the bottom. And what's shown in red is the amount of hydrocarbon that's actually calculated. So you can see by not correcting the resistivity appropriately, we're actually overestimating the amount of hydrocarbon in the reservoir. So something we just need to take account of when we're looking at RT measurements. And some of the other measurements that creep into Archie are AMN, RW, so cementation exponents, saturation exponents, formation water resistivity. So again, we get back to the Schlumberger logbooks, which we can use for estimating RW. Do we have things like formation water samples, etc. Or even just an example of a picket plot over on the right hand side. We can get M, we can get RW from this. But as you can see, there's quite a degree of scatter within those data points. Are we going to take one value for M, RW from this, for example? Are we going to use a range of M and RWs, or are we just going to use a best guess, so something like a 1, 2, 2, which is the general standard default? Does it actually matter at the Archie scale whether we're using 1, 2, 2, or do we need to have a slightly better feel for the different values there? The final component to Archie is the porosity that needs to go into it. So porosity is obviously calculated either core or from log measurements. Has the core being properly prepped? Is it intact, etc.? If we're using, so for example, if we're just using a density log, as I'm showing here for calculating porosity, bearing in mind we can use sonic and neutron logs as well. Have we got the appropriate measurements for the matrix densities of our rocks or fluid densities, remembering of course that the density tool reads the invaded zone, so we need to make sure that we know what the fluid is that the density tool's measuring. So different uncertainties that just creep in at each different little point of what we're trying to do with the calculation. So if I just jump on to the Archie equation, so I've looked at briefly each one of those parameters that sits within the Archie equation there. Does the uncertainty in any one of these parameters, does it actually matter? So let's have a look at the formation water resistivity RW. So these are some measurements which I've taken from actual data set, and if we actually just plot these up using a Pickett plot or whatever, or sorry, get these values from a Pickett plot or using the Schlumberger log charts, we can see that the range of RW values that I have there, it does provide a bit of a spread, not a huge amount, admittedly, within the SW values that we calculate, but that's just from RW. And remember, there are a whole bunch of other parameters in here which do have uncertainty around them. The interesting thing is that if we don't convert RW from surface temperature down to formation temperature, so the RW at surface temperature is 0.13, the downhole measurement is 0.02. If we don't actually convert that to the downhole temperature, look at the difference that we can see. We're getting what, up to about a 15% increase in SW that we're calculating there. So just a reminder that obviously we need to be making sure that the RW value is appropriate for the reservoir. If we then take a look at the cementation exponent, the value of M, for example, common default that we see in a lot of models is the value of 2, but it can vary quite significantly. So the example data set that I've been using here, the value is actually 1.7 that we have measured from core. You can see the difference again in SW that's calculated at that point between the M from core data, or just using a standard default of 2. So if you combine these two uncertainties together, we are actually starting to get a bit of an impact in our log calculation. So that's having a look at what can happen at the log scale, and but now what happens when we start moving into reservoir modeling space. So as geologists, engineers, petrophysicists, geophysicists, we spend a lot of time building reservoir models and hopefully trying to address the key uncertainties relating to our reservoirs through building a series of reservoir models. So generally some of the things that we're thinking about, so moving from left to right across the screen, we've got whether we're going to upscale things, which modeling algorithms we want to use, what's appropriate for the reservoir. This middle picture here of porosity is supposed to show a trend that's running through there. So are there any trends that we need to take account of? How are we going to be modeling facies? Are we using analogs? Are we just guessing the dimensions of any of our bodies within the reservoir? And then finally into implementing the saturation height function. Does that have any impact on the model that we've got? So let's have a quick look at the first bit, and let's have a look at some upscaling. So what I've done here is I've created a saturation height function from well log data. It's been built using the Cuddy foil function, which is just a plot of bulk volume of water against height above free water level. The BVW comes from porosity multiplied by water saturation. So I've created a height function derived, as we see the first of the pictures on the left, derived straight from the well logs. I've then upscaled my logs into what I've called a fine scale reservoir model, and I've created the height function at that scale. And then I have a slightly coarser model, the one on the right, which I've upscaled the logs into to again test the effects of what's going on. So we can see the difference between the 3 SW logs over here on the very left-hand side. So we've got the original log scale. This is the left-hand particular log. The very fine scale model is in the middle there, and the coarser scale model is on the right. And the key thing to remember about the fine scale and the coarse models is the fine model's got over 1 million cells in it. So if there's any reservoir engineers listening, apologies. You'll probably not be terribly happy with me if I give you a 1 million cell model. The run times on that, I would imagine, will probably be enough to drive people crazy. So that may not actually be fit for purpose, but it's just interesting to see what happens when we actually start modeling SW here. So what's the actual impact in the volumes that we're calculating here? So if we're using the fine scale, if we're using the well logs for calculating the height function and applying that, we get about 475 BCF. If we use the fine scale sector model, about 471, so not a big difference. That's about 0.5%. But if we use the coarser scale model, we get up to about 6.5–7% difference in SW, and that's literally just from doing nothing different other than taking the height function of log resolution and upscaling it into a reservoir model. So you can get up to about 7% difference in SW. So it's just something to, again, something to think about. Remember that, yes, there isn't a huge difference with this fine scale sector model that I'm calling here, but again, that's the 1 million cell model. That's a reservoir model that was probably not fit for purpose. So just by upscaling SW into reservoir model and deriving the height function of that scale, we're seeing about a 7% reduction in our hydrocarbon volume. So something else just to be aware of. Interestingly enough as well, if we don't actually pore weight the SW before we actually before we actually derive the saturation high function, again we get another change in the SW that's calculated. So it's about another 2.5% change there. So we've got to remember that when we're upscaling our SW, we've got to divide by porosity to pore weight that SW log. Otherwise, what we're seeing is not necessarily the correct answer. Okay, so that's having a bit of a look at upscaling. So where are we going next? What are we going to have a look at next? So we've had a quick look at whether we should upscale and create the height function at the log resolution or at the upscale resolution. Those examples basically use the FOIL function that was developed by Steve Cuddy, that BVW versus height plot, but that's just uncertainty within one particular function. So what about others? Remember, there's hundreds of different types of functions. Okay, not hundreds, that's an exaggeration, but there's the leverage A function, Cuddy, Skelt, Tholmere, Brooks, Corey, etc. Is there actually uncertainty within a particular function? And remember, of course, that there are other uncertainties that creep into the workflow. So the logging tools that we use, the logs that were generated, free water level depth. I'm remembering as well that when we're applying the height function, there can be porosity permeability dependent. So if we're changing porosities and permeabilities in the models, well, we need to be changing the height functions as well. So just a quick review of saturation height functions. I won't bore you for too long with this. I'm sure we're all fairly familiar, but we can calculate them at the core scale. So the good thing about that is that the saturations are directly measured using capillary pressure measurements. The thing we do need to be aware of is that scaling conditions in the lab are different to those of the reservoir. So as we saw earlier with the RW measurement, and remembering that we need to convert RW from lab to reservoir, it's a similar kind of deal with the core measurements. Logs, well, we're measuring logs at the reservoir conditions, but again, it goes back to those variations in electrical parameters, interpretation parameters. So as we saw with the value of M and the uncertainty around that particular value, again, that affects the way that we calculate the log-based saturations, that then go into the height function. And as I said as well, this is an exhaustive list of the different types of height function that are out there, but there's quite a few different approaches. Does it matter which one we want to use? So in trying to address that question of does it matter which saturation height function we want to use, I've done a bit of a case study just to try and make things a little bit more interesting rather than me just plucking values out of thin air. So what we've got here is a data set from offshore northwest Australia. It's a Crux field, a gas field. 4 wells have been drilled into the field, so we've got Crux 1, 2, 3, 4. I'm going to focus on Crux 1. This is the discovery well. So what we can see in the log track is we've got the gamma ray density neutron in the middle there, with a nice separation showing the gas. Good kick on the resistivity showing the hydrocarbons as well, and some core data as well. You can see by the red points, and these are just this is just the core porosity. But we've got core porosity, permeability. We've got the cap curves. We can see that there's a free water level somewhere down here, which is also confirmed by the pressure data. So we've got a pretty good data set, and we can actually begin to test different height functions. So what I'm going to do is I'm going to take a couple of the more common saturation height functions and build a few 3D reservoir modeling properties and see what happens when we have a look at the different methods. So the first method is Steve Cuddy's FOIL function. So it's just a cross plot of bulk volume of water versus height above free water level on a log-log plot with a power law regression, and the resulting function fit to the Archie data you can see on the right-hand side. It's doing a reasonable job at height above free water level, about 250, 200 meters. As we get down into the transition zone, we're perhaps not quite fitting the data as well as we would like to. So we might need to do a bit of tweaking of that function just to get a better fit there. Skelt Harrison, that's the next one. So that's basically this can be done on core data, on log data. Essentially, it's an exponential fit. So you have 4 fitting parameters, which helps you get really quite a tight fit into the data. So you can see that's doing a lot better job, I think, of fitting the data in the transition zone. And then we move on to the cap curve. So I'll just provide a bit of background to the capillary pressure data, and then we'll have a bit of a look at how to derive a capillary pressure-based function. So what we've got here, so there's basically the 12 samples that we had in the data set. So they're not varying much in terms of porosity, about 15 to 17%. One sample's at 21%. So I wouldn't necessarily say it's wholly representative of the reservoir. bearing in mind, if you look at the porosity track, we do have some lower porosity values, some higher porosity values than that particular range there, but we can go ahead and develop a function anyway. It's a good test because in reality we should be using multiple approaches for deriving a saturation high function, using both core, using both log data, and just trying to use as many different bits of data as we should. Okay, so let's quickly jump into our favorite reservoir modeling package, Petrel, and we can have a bit of a look at a leverage J function. So what I have here is just the Crux1 data that we can see. We've got the porosity track, we've got the ArcGSW and some core porosity just over here. With that said, we've got the capillary pressure measurements as well. So let's just go and have a quick look at the capillary pressure measurement. So if I just open up AVA saturation, this is just a tool just to help me build saturation height functions and build them just a little bit quicker, a little bit faster than jumping in and out of Excel spreadsheets. So what I have is, here's one I made earlier, saturation concept. And what this does is just got all the calculations, etc., that I've made before, already stored within this particular document. So I can quickly just revisit it and reperform the calculations. And if I've drilled a new well, for example, I can just whack in some new data to be able to see the impact on my saturation function. So all I've done is just selected the bits of my reservoir model I'm interested in, so the grid, the contact set, facies, porosity, permeability, etc. I know the normal formation is the gas bearing bit, so I can just choose those zones from the reservoir model, and I've got my reservoir model segments. And I've got the facies as well, so I'm taking out the non-net data as well for creating my function. And I can just piece those three bits together to create the function. So if I take the NOMA formation, I can take the reservoir segments and the facies, and I can group those things together to basically form to use all the appropriate data for calculating a function. So that's what we have here. So that's using those particular zones, segments, facies, and we have a variety of calculation methods. So the FOIL function, well, we've already had a quick look at that, and the Scout-Harrison function. So let's just stay with the leverage J method. We just choose the capillary pressure file we want to use, enable the well there, and then if we just click function, what we have very quickly is just a leverage J function through that data set. The regression constants are displayed below. So if I'm not too happy with the fit of that line, I can just quickly just shift that line around, just to alter the fit of that particular function, so we can test the uncertainty around the fit of the regression line through those data points, and go back to the recommended constants if we want to. It's then possible to apply that to the grid and the reservoir model. So you can see I've really quickly generated a saturation height function. So if I want to look at multiple approaches, I want to use my logs, I want to use my capillary pressure data, I can use as many approaches as I want and very quickly just build a bunch of 3D SW properties and run some volume calculations. So we're just applying now that leverage A function to the grid in the reservoir model. Now if I just jump into a 3D window, I can actually turn that SW property on. So you see it's stored within Petrel here, and we have the SW property available within Petrel, and that looks pretty nice. We can start taking that forward into volume calculations. The history settings within the property itself actually store the function that was used to create that particular property. So again, we've got the audit trail preserved there. We can revisit this whenever we need to. So that's just a quick flavour of what we can do within AVA saturation. What we can see is this is so that's the resulting function, and we've built that using all 12 of those core samples. What we can also do, and I can do the same thing within AVA saturation as well, if I just jump back, and I can show you the porosity banding. So we can choose banding type, and we can choose porosity, and then we can sort of select a porosity range that we want to use. Whoops, it's up to 16%. So we can now actually begin to split our reservoir model down by porosity class. And that might be important if we do have a full range of porosity and the functions do start to look different. So what I've done is I've broken them down by the 15, 16, 17% porosity class. And I've actually developed functions from oversaturation for each one of those porosity groups. Bearing in mind the scale on the function here is to 0.2, it's not to 1. I had to put it at 0.2 because you can't actually see the difference between the functions. And if we look at a correlation between each of those functions, it comes out about 99, well, near 100%. So there's very little difference between a function derived using each of the porosity groups. So we're good to use use all the data to generate one particular function. Now, there's probably a few reasons why the functions don't vary too much. Remember, the core data came from quite a way above the reservoir, right above the free water level, sorry. So it was at a reducible saturation. So we're not exactly going to expect too much difference in those functions. But what actually happens when, in the real world, what are we actually interested in? Why have I looked at different height functions? So on the left-hand side, we can see the Archie saturations in blue, and each of the height functions I've calculated in a different color. So we can see the fit to that original data. So we can see the foil function in green, we can see Skelt in red, and we can see the Leverett J in orange there. So we can see the Leverett J function is really going to over-predict the amount of hydrocarbon close to the free water level. Skelt's probably doing a good job, and the foil function could do slightly better in the transition zone. But what this actually means is if we take a reference case gas in place for this particular model, so that's using a constant SW, just gives us a ballpark estimate for what we think the gas in place is. We can look at the foil function gas in place there. That comes to about 450 BCF. We get to about 470, 480 with Leverett J, and Skelt Harrison's a very similar amount. So just by looking at three different saturation height function methods, we get about a 12% difference in gas in place, and that's only just by changing the function that we're using for modeling SW in our particular reservoir models. So that just gives a flavour for what can actually, for why we should be using different height functions, why we should spend a bit of time investigating different ways of modeling SW in our 3D grids, why we should actually be using a combination of different methods. Maybe we want to use one height function for a particular fault block, another height function for a different fault block. We just need to be investigating which methods provide us the best fit to our data and which methods are actually, we're comfortable with, and make sure that we do investigate these sorts of uncertainties, because, we've seen all the way through that that uncertainties in the electrical parameters, uncertainties in upscaling, and now uncertainties in height function can all compound themselves. As I mentioned at the start, so what else can we do with these saturation height functions other than just model SW? Well, we can use them to actually begin to look at and predict the depth of the free water level. So let's imagine a scenario where we have only an oil down to or a gas down to, and we don't actually know where the free water level is, or say there's some uncertainty around that particular free water level depth. The height functions can actually be a useful QC tool. Okay, so if we go back to Crux 1, we've got the well logs on the left-hand side here. I said earlier that this pressure data is telling us where the free water level is, but just forget I said that for now. Let's just ignore that. Let's pretend that we don't actually know where it is. So if we're looking at the logs, and I've zoomed in a little bit here, there's a bit of a range that we can have a look at for where the free water level might possibly be. So what we can do is calculate the saturation height function at a specific depth increment across that range, so every 1 meter, 2 meter, 3 meter, etc. We can then, using those saturation height functions, we can then develop a predicted saturation log, compare that back to something that we consider to be accurate, be that Archie, be that NMR's, core, capillary pressure, whichever. And then we can actually begin to say, okay, well, which height function is going to give us the best fit to that original data, and that is a proxy for where our free water level might be. So these are just 3 examples that I have here for the mid-case, shallow, and deep free water levels. So we can see there's a bit of a difference in the data that's available there, and really quite a difference in the fit of the function, particularly with the deep one. So what I have on this particular slide is, okay, I'm comparing each of these predicted saturations back to the original data. So in the plot on the left-hand side here, the original data is my Archie log, which is shown in blue, and my predicted saturations are shown in red. So we can see at a reasonable height above the free water level in the shallower reservoir, we've got a pretty good match to the original data. As we get closer to the free water level, the differences start to become more apparent between those methods. And what we can do then is create a correlation between each of those logs, and then plot those correlation coefficients versus depth. So that's what I've done on this middle slide here. So we've got a possible free water level range at about a 95–96% correlation coefficient between the predicted saturations from a height function and the original log-based saturation. So maybe that's where our free water level sits. As I said, there is actually some pressure data available for this particular field. So the free water level is actually at 3867 meters subsea. So there's some pretty good pressure data, as you can see on the right-hand side. And where that free water level fits, well, it's, conveniently that's smack within the range that we've predicted using the height function. So, what that tells us is that, in the event that we don't have any pressure data, or we've got unreliable pressures, we have just down twos within the well, we can quickly begin to estimate where the free water level might be. Or in an exploration setting, for example, we can quickly develop some height functions and put a range of contacts on the volumes that go into our exploration volumes. So just a few conclusions from all of that. So well, what we've seen is that there are quite a few uncertainties. So albeit there are smaller ones within the log interpretation. So for example, within the electrical parameters. So while these individually they're quite small, there are quite a few different uncertainties. So there are 5 parameters in the Archie equation alone. So it's worth spending a bit of time looking at and assessing each one of those and what impact there might be or what impact there is on the log SW that we calculate, and whether it's critical. Looking at whether to upscale or not, so it's prudent to do so, especially when calculating saturation height function. But some of the errors within upscaling can be small, depending on grid size, obviously. But the key here is that poor volume weighting of the upscaled SW log is something that we need to remember to do. And then individual saturation height functions. So each one of those has uncertainty associated with it, mainly due to the fitting parameters, and there's uncertainty between each of the methods, whether we're using logs, whether we're using core, for example. So we should be considering using multiple approaches in our models. Maybe one fault block fits better to the Cuddy function, another to the Leverett. And this is something that we should be looking at, spending a bit of time doing and testing different ideas and spending time with our data and seeing which functions give us the best fit. And finally, we saw that that in situations where, say, the pressure data is unreliable or we don't have any, we can use height functions to actually give us an estimate of free water level depth ranges, and that's just another use of these functions, another reason why we should spend a bit of time looking at different height functions, different approaches. But it's always key to compare back to core data, log data, NMR values, validate against pressure data where possible, and begin to tie all that information together to begin to tell a bit of a story. So thank you very much for listening. I hope you found that interesting. I hope there were some useful takeaways and some things that's given you a bit of food for thought. Yeah, thank you for listening. And if you've got any questions, please ask away.
Thanks for presenting today, Matt. It's been really great to see how we can use oversaturation to quickly and intuitively calculate multiple saturation height functions. We'll go ahead and take some questions now. Just a reminder that in order to ask a question, please make sure you type your question in the question box in your GoToWebinar control panel anytime now. We'll allow you a couple of minutes to type those questions out, and then we'll start taking a few questions. It looks like we have the first question, and I'll just read it out for the benefit of everyone else on the webinar. And the attendee asks us to please elaborate a little bit around how and if we would handle tilted contacts and reservoirs in ambition within your plugin. So that's within oversaturation.
Yeah, very good question. Thank you. Okay, so let's handle the first bit first, because the tilted contacts piece at the moment, that'll depend on how you've actually handled the tilted contact within the grid. So Yeah, interesting question. I think that would basically be a case of breaking the model down by reservoir segment, for example. So if your tilted contact sits across multiple segments, you'll just have to use different segments of the reservoir model. So I'm not exactly sure how you'd put a tilted contact into Petrel. The second part about the ambition, so we're a relatively new plugin, so what we're working pretty hard towards at the moment is to be able to build in this functionality to support that, as well as other reservoir engineering parameters as well. So what we want to come towards supporting is rel perm calculations, and be able to basically get a good consistency between rel perm curves and the saturation height function, just to make sure that the height function and the rel perm curves are agree, especially when we get to a reducible level. So hopefully that answers your question. Thanks.
There's someone who has raised their hand to ask a question, which involves asking that question verbally. So I can, of course, turn on the microphone, but alternatively, I wondered whether that person wanted to just type their question into the question box instead. We've also had a question about how highlighting how the different methods is done, and in particular, how much difference does it make in oil reservoirs?
Yeah, so that's a good point. Basically, yeah, height functions work particularly well in gas reservoirs. There are quite a few other things you need to take into consideration when modelling in oil. So I would expect we saw about a 12% difference in gas. So we would need to look at oil reservoirs as well. We'll expect perhaps a bit more of a difference, and of course as well, if we've got say an oil reservoir with a gas cap as well, we need to remember to split those two out. We can't model the saturations together. So again, yeah, it's another good example, I think, of why we should be looking at different functions and considering different approaches.
And following on from that, Matt, the same attendee wants to know, how does it change in carbonates? And can we only choose the best method and then get an uncertainty? Or do we need to use... that question is unfinished, actually. So how does it change in carbonates?
I think I understand the second point of the question. Can we choose the best method and get an uncertainty? Yeah, okay. Does it change in carbonates? Yes, again, you'd need to consider the same approaches. We can use high functions in carbonate reservoirs, and it's considering a similar going through a similar sort of approach. Can you choose the best method and get an uncertainty from that? Yes, indeed. But you see there is quite a bit of a scatter around the data points when we fit the regression through that. So depending on how good a fit you feel the line is, you can begin to then shift that regression line up and down. That's why in saturation we allow you to change the regression constants. So you may want to shift the regression line around, and that in itself, just on one data set, that will give you a sort of a low, mid, high case just from one data set itself.
Great, thanks, Matt. Someone else wants to know if we need to use the saturation height approach if it is not a tight rock with long transition zone and a contact is evident in the logs.
Yes, because the reason why using a saturation height function is to model the saturations appropriately within your reservoir model. So kriging or using Gaussian simulation to model SW is not correct. You end up with a cell with 10% SW against a cell with 90% SW. So the reason why we're using the saturation height functions is to apply the SW correctly following capillary pressure theory.
Okay, moving on to the next question is, how can we model SW in a gas reservoir with no free water contact and multiple sands with few which are low in resistivity?
That's a challenging question. Thank you. Yeah, basically, I think the height functions are not exactly going to be the biggest concern, I don't think, when you're looking at a reservoir with low resistivity gas sands and multiple sands like that. I think there's going to be a lot of time that you'll need to spend actually looking at the logs and trying to actually distinguish where you do have gas, where you don't have gas. Are these sands in communication? If you don't have a free water contact, then you might want to run a very quick height function just to try and guess where that contact is. But yeah, that's a really tricky problem.
So someone else would like you to talk a little bit more about pore volume weighting.
So the pore volume weighting, so that is just when we upscale the SW log, we just need to make sure that we divide that or weight that by porosity, because SW is a porosity dependent property. So that does change the average SW that you then put into a cell if you don't pore volume weight it.
The person who asked about ambition said they'd like to have a bit more feedback offline. So at the end of the webinar, just for everyone's benefit, we'll give you some contact details for Matt so you can reach out to him. But we also have all your contact details as well. So we'll make sure that we'll reach out to you specifically to continue that conversation. Someone wants to know if the Ava window plugin can be found in the Ocean store. They can't remember seeing it in Patrol previously.
No, the Ava plugin is not at the moment within the Ocean store. If you're interested in taking a look or having an evaluation, we can certainly accommodate that. As Laura just said, we'll stick my contact details up at the end of the meeting, and please do drop me an email, and we can arrange a separate call, and we can certainly give you a trial or an evaluation period.
We've got another question asking how we might find uncertainty when we don't have an FWL, rather we have a shale oil contact.
Oh wow, that's I'll have to be entirely honest. I don't know the answer to that question. I've very limited experience in unconventional, so I'm not. I'd have to look at that and come back to you offline on that one.
And what seems to be the final question for right now is whether we'll be sharing the presentation around. And yes, I'll also touch on that in our final slide in a few minutes. But this webinar will be available online on our website in the next few days. But all attendees today should also receive their own copy via email within the next 24 hours or so. I think there's one final question. Oh no, that was it. So I'll give you all a chance to ask any final questions you might want right now, and if not, we'll proceed to wrapping up. Well, that seems to have covered all the questions that you all had. Thank you for a really lively discussion and for putting forward all your questions. Matt, before we finish up, is there anything else you'd like to add?
No, nothing further from me. Just a final thank you to everybody for your time this morning. Thank you for listening. Thank you for the excellent questions. If you've got any other questions, you can see my email address is here. Please do feel free to email me and get in touch. I'd be more than happy to talk to anybody. And
yes, just a thank you from me for joining our webinar. We really do appreciate you taking the time to join in this session. A reminder that this webinar has been recorded and all attendees should receive a copy via email in the next 24 hours or so. If you have colleagues who weren't able to attend, we will also be making this webinar available on our website very soon. And also a reminder that over the next 4 months, we're pleased to offer a further 4 webinars, which will showcase how multi-scenario modeling can be intuitive and cost-effective, while at the same time providing better representation of reservoirs and better volume estimations and optimized well placements. To see the webinars we have on offer and to register for your spot, please visit our website. And you can see the link to access those webinars just below. It's also the page that you would likely have visited to register for this particular webinar, so just return to that if you are interested in registering for any of our other sessions. Thank you for joining us today, and we look forward to seeing you next time.